Okay, hello everyone, this is LN. Today I would like to talk about second harmonic generation, which is our experiment 6. In this experiment, we would like to use several different kinds of crystal, and the two main parts are the uniaxial and the biaxial, which respectively are we will use the non-critical phase matching and critical phase matching technique. So actually, for uniaxial and biaxial, the technique and the theory are literally the same, but biaxial is just harder for us to use because uniaxial allows non-critical phase matching, which is easier for us which gives us larger error or the angular bandwidth and temperature bandwidth for us to generate the second harmonic generation. And also in previous, we also usually discuss about the non-depleted pump, which is the low efficiency. And in this experiment, we will also see that how the efficiency, when the efficiency goes larger, and how it affects our second harmonic generation. So the first part, we would like to start from a relatively easier uniaxial, which is a little nail bait. And usually to prevent the photoreflective effect, we will use the magnesium or the Zn to fill the defect. Nevertheless, the main thing we need to know here is that the nail bait is a negative uniaxial material, which means that its extraordinary index is usually smaller than the ordinary index. And thus, we will see that in terms of the phase matching condition, we will see that usually it's always larger, but at a certain angle, they will finally be the same, and this angle is called the phase matching angle. And for the nail bait, we like to use D31 as a nonlinear effective coefficient due to its relatively large value. And note that the 1 here actually is the L index, which 1 corresponds to 1, 2.22, and so on. So thus, to induce 3-1, we need to use rather 1-1 or 2-2, which is the X polarization from fundamental wave in X polarization and in Y direction. So here are the basic picture we will use. And with this basic picture, there are some things that we need to do in this experiment. First is to identify the optical axis, because we need to know that because the polarization matters. And the second is that how the power of the single harmonic generation varies with the temperature and incident angle, which corresponds to the phase matching condition. And the third one is to redo it. That the first we are using actually magnesium dope, and then we will next use the Zn doped little nail bait to see how the conversion efficiency changes with the crystal length. So for the first part, to identify the optical axis, we can utilize the isogeo pattern, and this is a result from the polarization rotation of incident light through birefringent crystal. And in this experiment, we need to know that if it's uniaxial crystal cut perpendicular to the optical axis, like this, and this is OA, and it's cross-polarized, then the pattern will look like this. So that is to say, our experiment setup is relatively simple, since first we need to know that our convention to set Z along optical axis and to set two polarizer to be cross-polarized. And if we can find the crystal, and by rotating the crystal here, if we get this picture at the screen, then it means that the Z-axis is the optical axis. For second part, we need to know how the power varies with temperature and incident angle. and this will gives us an important parameter, which is the how the ratio of the second harmonic generation versus the fundamental wave conversion efficiency. But before knowing that, we need to know what's the fundamental power inside the crystal. So that's what we derive here. And to measure it, because the output of the crystal is actually 1060, input at 64, and output will be 1064 and 53. So we need to use a high reflective mirror specifically for a specific wavelength to separate these two kinds of power, and then to measure the transmitted power and thus induce what's the power inside. But since there may be some errors inside, we can take into account about the Fresnel's reflection loss to measure, to correct the exact transmitted power outside the crystal. The second thing to measure is so by knowing the fundamental power inside, then we can know, next we need to see how the temperature affects the SHG power. So just as what we have read before, for non-critical phase matching, it has a refractive index. Both ordinary and extraordinary have this kind of relationship, which this gives larger error rate. So in this experiment, we would like to just typically set our propagation vector along this direction, and by modifying the temperature to see how this phase mismatch will occur, which in turn changes the SHG power. And this will be a sinc function if it's a low efficiency case, which we have learned from the nonlinear optics course. And yeah, this is the part of it. And the key point here is that we need to make sure the laser is parallel to the horizontal plane, so we can just purely modify the temperature. And the second part, and another part, is just literally the same as previous, but instead of temperature, we are now modifying the angle. So here we also like to make sure that it's already along the non-critical phase matching, and we just by modifying the angle here to see that how the output sinc function is. And since we already know from low efficiency it's actually a sinc function, so we will fit our data into the sinc function and to see that what's the exact output. The third part is to see how the conversion efficiency changes with the crystal length and the acceptance bandwidth. So a typical picture shows a relation is this. So you can see that as the peak efficiency goes larger, the phase mismatch region, which is the acceptance bandwidth, actually goes lower. And this is because that as the conversion efficiency goes larger, which means that at the end of the crystal, there are more second harmonic wave, which it may cause a back propagation, which will affect our collinear phase matching condition because it's actually in a different direction, which makes it strict, makes the acceptance bandwidth narrower in this case. So for a specific formula, you can see that the low efficiency, it's actually a sinc function, and it can be seen that as the crystal length goes larger, the sinc function, never mind. So here is just the concept. So the larger conversion efficiency causes a back conversion, and thus the phase matching condition, phase mismatched, and the bandwidth is become lower. So the experiment setup is actually as this. So the crystal orientation really matters because from the first part we know where the optical axis is, and now we would like to generate. So recall that we are actually generating a z direction polarization because we are having a D31 as our nonlinear coefficient. And to specifically just use one, we use the polarization along y direction. So it actually y here. So correspond to the second D31 here. So we can see that here it's actually the polarization is actually the y direction. Okay. And the optical axis of the crystal is not the z along the propagation, but here, because the propagation is along x direction, because we already specify our polarization along y direction. So we have no choice but to set the propagation vector along x direction. And to measure the power at the output, we need to use the high refractive along specific wavelength. In this case, it's the 1064 to separate these two different wavelengths. And then to use the fault detector to see the power and to correct the power using Fresnel reflection. So here is just a reminder that we are using a first type phase matching, which is OO to extraordinary, and the two fundamental wave we set to be Y polarization, and the induced polarization is along Z direction. So in practical case or in our experiment, we all want to improve the power, so we need to maximize our effective coefficient. In this case, it's D31. And so there are some degree of freedoms in this kind of space, but for the incident angle theta, it's already fixed due to the phase matching condition. But if we take a close look at this 3D plot, we will see that actually there's another extra parameter phi that we can use to alter it without modifying our phase matching condition angle. Excuse me. And thus, by changing or rotating the crystal along phi direction, we would finally find a larger power, and this is the ideal case for this little Nile-based crystal. And just to note that since our induced polarity is on z direction, and thus the extraordinary is actually the pz cosine theta pm. Oh, it's 90 degree minus theta, so it's actually pz sine theta, which means that in a phase matching condition, which our theta is actually along y direction, or x direction rather, because due to different phi, but it's just perpendicular to the z axis, and thus the extraordinary polarization will just be the z polarization, the polarization along z. So this is just a small tip to see, to maximize our effective coefficient and thus the conversion efficiency. Excuse me. Thus, so the above is all for the uniaxial, and for biaxial it's actually literally the same, but with different kind of crystal and different kind of parameters to see. And one thing to notice is that for biaxial because there are it's not the uniaxial like, so there's the optical axis already fixed at specific place, and thus the phase matching condition is already fixed. It's not like the uniaxial, which we have this kind of non-critical phase match. Thus, in this case, we may not have the same degree of freedom as uniaxial phi to modify without modifying the phase matching condition. And in this KTP crystal, we will use the type 2 phase matching, which is the OEE, or EOE rather. And the effective coefficient can be calculated as following, where the matrix representation is as shown here. And the thing to do in this part is literally the same. Of course, we need to know where the optical axis is, and with the optical axis being clarified, then we can use the different polarization to induce our desired simple harmonic generation. But there's something more to derive in this experiment, is that we may need to derive the laser waist radius. And to derive the laser radius, we need to know that, so in this crystal, so this is a crystal, and actually the Gaussian being inside, no matter you are first frequency or the 2 times the fundamental frequency, they will have the same Rayleigh range. So using this concept, we will finally get into this conclusion, where we may see the power of the second harmonic, the polarization of the second harmonic generation and the first harmonic generation have this kind of relationship, where the effective coefficient is known as calculated here, and the frequency is known, the refractive index of course is known, and thus we can derive the laser waist radius for here. Okay. And the experiment setup is as shown here, where we also, it's like similar as previous because it's really the same. And note that the 3-axis stage is for us to create more freedom for us to slightly modify the angle and to see how the acceptance bandwidth varies. And also by measuring the change in the temperature inside and measure it to see that how the temperature acceptance bandwidth affects. And to deduce the conversion efficiency, we need to know the fundamental power. So we need to separate 2 different wavelengths and to measure each power respectively. And also, there may be some measure loss, so we will use Fresnel refraction to correct our measured value. And also, we will use a polarizer to see that what is exactly the polarization of these waves, because unlike uniaxial, where the optical axis is along z direction, the biaxial has the optical axis not directly at the z, y, or x direction. So it's rather complicated to measure. It's rather complicated to represent, since we need to have a theta and phi to represent it. Okay, so that's it for my presentation. And so to have a simple conclusion is that This is an experiment just mainly to measure the simple harmonic generation power. But before that, we of course need to know where the optical axis is to let us know where the relative polarization of the fundamental wave and the SSG wave. And of course, due to the phase matching condition, there's a temperature acceptance bandwidth and the angular acceptance bandwidth. Also, because in our previous analysis, we always assume low efficiency. So in terms of high efficiency, where larger crystal length may induced, this would cause back conversion, which affects the phase metric condition. And note that in terms of temperature acceptance bandwidth, we will see that, especially just for the usual green light laser, this is relatively large, and thus with short L, we have large delta T, which means that the usual laser we use in our daily life doesn't really cares about the temperature to fix the temperature at a specific point because it has large delta T. Yeah. So that's it for today, and I hope you guys can have a brief understanding about this experiment, and if I have anything wrong or anything more to be added, please feel free to tell me and discuss. And I apologize for my absence in this pre-meeting lab, but I'm always available online. So yeah, thank you. That's it.